Hi, everyone. Welcome back. Up next, we have Vladimir Vukicevic. Vladimir has been with Mozilla since Firefox 1.0 with a focus on graphics and media, which led him to the creation of WebGL, which is the standard API for 3D graphics on the web. These days, he's involved in enabling developers to maximize performance out of the web apps across all platforms. And here to show us some of his work, please welcome Vladimir.
Hello? There we go, okay. So thank you. Had I known that that was gonna be read out loud, I would have probably written something a little bit wittier in that introduction there. So I'm Vlad Vukicevic. I'm right now an engineering director at Mozilla. For the past year and a half or so, my focus has really been on high performance web apps, figuring out how to squeeze the last bit of performance possible out of the web, and also how to take things to the next level to make web apps feel closer to native apps, both in capabilities and in performance.
Just bring it a little bit closer.
Bring it a little bit closer, okay, as long as it doesn't fall off. All right, is that better? Maybe? Okay, good. So, one of the things that we've at Mozilla have been heavily involved in is bringing games to the web. So I'm actually not going to talk about games here today, but I'm going to talk about one of the technologies that we're using called asm.js. So overall through the day, excuse me, not through the day, but through this presentation, first I'm going to go over what is asm.js. I'm sure some of you are already familiar with it, so this is going to be fairly brief, but just it'll be a quick overview of what we've actually done with asm.js. I'm going to talk about writing asm.js by hand, whether that's possible, why you might want to do it, and also probably the many reasons why you wouldn't want to do it. And then we're going to talk about using Emscripten, which is a tool that Mozilla has for compiling C and C++ code to JavaScript and to asm.js, and for how you can leverage that in regular JavaScript applications. So not in kind of full-scale C and C++ apps, but just as components of existing JavaScript applications. As part of that, we're going to talk about how you can integrate some libraries, and then I'll give some ideas of what you can possibly actually do with this technology as part of existing web apps. So first, what is asm.js? Asm.js is an optimizable subset of JavaScript, and it's intended mainly as a compilation target. What this means is basically that it's not really intended or designed to be written by hand, but it is just JavaScript. It's JavaScript with a few extra annotations and some more information that can be given to the JavaScript runtime and the compiler to really make it very explicit what the intent of the code is. So this is an example of asm.js. It looks just like JavaScript, except there's some extra little squiggles in there. There's a lot of extraneous or zeros, there's some extra plus signs, things that you would not normally write, but that are essential to asm.js because they're part of the rigid rules of asm.js. These things inform the compiler whether you want a variable to be an integer, or whether you want a particular operation to be executed as to floating point operations, like whether you want integer division or floating point division, whether you want to access some data as an 8-bit integer or as a 32-bit integer. All of these things are encoded in asm.js. Though again, it's fully compatible with regular JS. So an engine does not need support for asm.js itself. And in fact, right now, the only engine that has explicit support for asm.js is SpiderMonkey, the engine in Firefox. The V8 folks are interested in asm, but they're not committed to supporting the explicit use asm kind of pragma language. Instead, they're doing optimization work based on asm.js itself. So for example, just recently, the Octane benchmark got a new benchmark added that is a bunch of asm.js code in there. So they're interested in this type of approach, but again, they're not committed to supporting kind of full use asm, although of course, I hope that they do that because there are some advantages to that I'll mention in a bit. So asm.js operates purely on a heap, purely on a single array buffer. So you have to allocate a bunch of memory up front, and that's the memory that asm.js can work with. It doesn't have any notion of objects or strings or anything like that. It operates only on numeric values, and it can read and write those from the heap, it can read and write those from local variables, and they can be passed around through functions. But again, there's no strings, there's no JavaScript objects, there's no nice hash maps, things like that. You don't get any of those. So it's very low level. And there's a reason why it's called asm.js, because it's much closer to assembly language than it is to something like JS. kind of the full high-level language. But of course, you're not writing assembly instructions, things like that. There is some structure around it. So it's kind of a middle ground there. asm.js can call regular JavaScript. This is how asm.js code can interact with the capabilities that the browser provides. So for example, if asm.js wants to interact with web audio or with WebGL, or if asm.js wants to perform an XML HTTP request, it can do so by just calling out to regular JavaScript. You can provide any number of functions for it to call. You give the asm module all those things up front, and then it has access to everything that kind of the browser would normally provide it. Likewise, asm.js code can, of course, be called by regular JavaScript. Many of the kind of the large-scale demos that you might have seen, such as the Unreal Engine 3 demo, that's an entire app running in asm.js. And the way that the browser interacts with that is it's really request animation frame. There's one draw function that's exposed from asm, and that's kind of the entire loop. That's it. But it doesn't have to be that kind of monolithic. You can expose many functions to regular JavaScript that'll do processing, that'll do all sorts of things that are running within the asm module that gain all the performance benefits, but you can still do the rest of your application in regular JavaScript. And because of this, asm.js can provide predictable performance. So like I mentioned, there's no objects, meaning there's no garbage collection. There's no garbage ever generated inside an asm module. So any code that's executing within asm will never have any GC pauses. That's of course not true if asm calls out to regular JavaScript, because at that point you're back in regular JS world, you can generate garbage, GC can happen, all these things can happen. But while you're inside the asm code, your performance is very predictable because you generally know how things will execute. Doubly so if the engine explicitly supports the use asm pragma, where at that point you can roughly even estimate the performance it'll run, even compared to the original, especially whether it's C and C++ kind of native code. If the engine doesn't support the use asm pragma, performance can still vary a little bit because the engine is still doing a lot of the inference work that asm it's trying to really infer the information that asm already provides it, like whether something is a number, whether something will always be used as a double, things like that. So performance can still vary a little bit, but even asm code in something like V8 runs faster than kind of the non-asm code. So there's really two ways to use asm.js. The first one is what we've seen a bunch of demos from Mozilla and from others do right now, which is to bring existing C and C++ apps to the web. The current kind of very flashy demos do this because, especially where games are concerned, games demand a lot of performance. They demand a lot of capabilities from the platform. They demand a lot of assurances. To hit 60 frames a second, you have to be able to do a lot of work within 16 milliseconds, every frame consistently. If you can't do that, you get janky frame rate, you get a bad user experience. So that's one of the reasons why we kind of chose games as the first target here, because it sort of really proves out what's possible. If you can do games, especially kind of high-end 3D games, then you can do a lot of other things as well. But that's actually not what I'm going to focus here today. Instead, I'm going to talk a little bit about how you can use asm.js to accelerate the processing of existing JS apps. Using asm.js, and especially using tools like Emscripten, you can leverage many existing libraries, especially open source libraries. You can offload and speed up a lot of data processing, analysis, image processing, whenever you actually have any kind of chunk of data to do something with, doing it through asm, potentially through a C and C++ library, something like that, becomes a possibility for added performance. We'll talk a little bit about, towards the end, some examples of what you could do with this that would be difficult to do with kind of existing JS code today. So how do you write asm.js? Well, you can write it by hand. This is actually readable on the screen there. Well, readable. Sort of readable. It's pretty verbose. This is a simple asm module that just averages a number of floating point values together. This is actually a fully complete sample. You can run this and it'll do the right thing. Again, it'll do the right thing in all browsers, whether they support asm explicitly or not. But it's not very pretty. There's a lot of things that are sort of convention, a lot of things that are rigidly defined by asm.js. And it's not really what you want to be doing by hand. So you can write it by hand, it's doable, but it's pretty painful. There are some cases where you might want to consider it. So if you're doing something fairly simple and especially fairly numeric, like if you're writing a matrix math library, it makes sense to think about whether you might want to use asm.js directly by hand for kind of the extra control for having direct control over exactly what operations are being executed. But like I mentioned before, asm is intended to be a compile target. Now, not just from C and C++. That has been kind of one of our focus because that's where there's a very large body of code already out there that we can help bring to the web and take advantage of. But there's other languages and other experiments that are also targeting asm.js. LLJS is something called low-level JavaScript. It's a project by a Mozilla employee to provide JavaScript with some additional type annotations. So you can declare something as an integer, much like you could in something like C or C++ or C#. And that information flows down into the generated asm.js. But it's also much closer to JS itself, so you can actually write much more natural-looking JS. The folks behind TypeScript are also interested in generating asm.js, as are actually a number of other groups. Asm.js is emerging, and there's a lot of interest in using it as a general VM for the web, for any kind of language to be able to target this VM. So there's experiments going on with Python, with Lua, with C#. Of course, I mentioned things like TypeScript, with Ruby. All of these languages are looking at ways to let their users write in those languages and still be able to get their code on the web. JavaScript has kind of emerged as really the only web language. It's unlikely we'll see another one gain kind of wide popularity in the web. But it turns out that you can use JavaScript as a VM to bring whatever language the user prefers to use to be able to put their code on the web. And then, of course, we have Emscripten for C and C++ source. Emscripten is based on LLVM and Clang, which are popular C compilers. Apple has done a lot of work on them. They're kind of the default compilers on OS X or on iOS. And they form the basis for Emscripten, where we use the same optimization passes, all of the same pieces of LLVM, and only in the final step does it go through Emscripten where we actually generate JavaScript and generate asm.js. So let's talk about how you can use some existing libraries through Emscripten. There's a lot of C and C++ libraries out there, whether open source or closed source. So just kind of in the open source world, here's a couple of examples. There's something called OpenCV for computer vision. This provides, amongst many other things, things like face recognition, face comparisons, and there's a whole bunch of, this is kind of a toolkit for computer vision. Something like this doesn't really exist in the JavaScript world, but these things are the equivalents to D3 or to jQuery of the JS world. For physics, you've got something like Bullet. For compression, there's zlib, LZ4, all of these different compression algorithms tailored for different uses, different kinds of data. Whereas currently on the web, you're kind of limited to some kind of very narrow, very specific uses. There's libraries for text-to-speech. eSpeak is an open source text-to-speech library. There's libraries for geometric data computation. Something called QHAL is kind of pretty much an industry standard for doing these kinds of things that you would not really think to do in JavaScript or even to think about having access to these things on the web, like text-to-speech in JS. Like that sounds crazy, or that sounds like somebody's interesting hack, but maybe not really feasible for kind of real-world usage. But it turns out that it actually is. And so you can kind of add a lot of these things to your toolbox when writing kind of regular JS apps. Many of these already have Emscripten ports. When Emscripten first came out, and especially when the performance provided by asm.js was really starting to be proven, the authors of these libraries or people who are kind of heavily using them started looking at ways to compile them with Emscripten, made some of the few necessary changes. In many cases, they actually created some nice JS layers and JS wrappers around these so that you could actually have a nice interface. Even accessing kind of an asm.js C++ module from JavaScript, it's a little tricky, it's a little bit gross. But you can write a nice JS wrapper around it, and at which point it starts to look a lot more like your typical JS library with some nice helper functions, things like that. So the overall path for integrating with asm.js code, or with an asm.js module, as we call it, there's three kind of main steps, and you always kind of go through these steps. The first one is you have to get the data into the asm.js heap. Like I mentioned at the beginning, asm.js operates only in numeric values, and it only interacts with its own heap, its own set of memory, its own kind of, its own kind of buffer that it uses for memory. So for example, in this case, if you wanted to pull some image data out of a canvas, to give that to an asm module, you have to actually copy it into the asm.js heap. This is actually really unfortunate because this is kind of all this extra copying back and forth is an inefficiency, both when using asm and kind of in the web stack in general. One of the things that we're looking at Mozilla is identifying places where this exists and figuring out a way if we can add some new APIs to the web where you can explicitly say, get some image data, but put it here. Put it into my existing array buffer. Make an XML HTTP request, but when you read the data, read it into my existing array buffer so that you don't have to access, you don't have to have 2 copies of the data and use up all that much memory just to be able to get it into the asm heap. So you call getImageData, you get your image data element, and then you have to call malloc on kind of the global asm module. This sounds and looks totally bizarre to JavaScript programmers, right? Like because you're doing manual memory management here. But that asm heap, especially if you're coming from C and C++, that's just like a system's memory, and you have to allocate and release things very explicitly there. So you would allocate some memory for where you're going to copy this data in. You do the copy, and then you can actually make the function call to do the processing. You give it the pointer, again in kind of C and C++ world. In this case, in JavaScript, this pointer is just a number, but that's all a pointer ever is. All you're saying is, at this offset in my array buffer heap, that's where my data starts. And so you hand that off to the processing function. It does whatever it does, modifies the memory that's there, and then you do the reverse process. You have to get that data back out of the heap. You reset it back onto the image data. You have to make sure to free that memory. Otherwise, again, you have a limited heap. If you allocate, say, 16 megabytes of that heap and you're processing 1 megabyte of image data every time, you do a dozen processes and you're going to run out of memory unless you're actually careful about cleaning up. So just like actually in the earlier talk, there was a lot of talk about garbage collection, memory management, things like that. In asm.js, you have to deal with manual memory management, manual allocation. But if you're writing high-performance JavaScript, if you're trying to optimize things very heavily, especially for very long-running apps, you're already really thinking about these things. You're already doing a lot of this in JS, but just much less explicitly. There was a question earlier about, in browsers, do you get to control garbage collection? Do you get any kind of insight into there? And unfortunately, yeah, the answer is no, because for a bunch of reasons, some of them good, some of them bad, you don't really have much insight into what the browser is doing when it's garbage collecting, what it's doing, how much time is it spending, all of these things. With asm, there is no garbage collection, so you have to do all of this stuff yourself, which is a pain, but it does give you also a lot more control. That's usually kind of the trade-off. More control, you have to take care of a lot of more things yourself. The nice thing is you can always write some wrappers around the asm code. Again, like I mentioned earlier, make it look a lot more like regular JS, and never really have to think about this again. So for example, for the previous code, you might have a function called processImageData, which will just wrap all those 3 steps together. But once you write this once, you never really have to think about this again. The rest of your JS code can just use this processImageData function, never noting that it's implementing inside asm. You can change the implementation of it later on. You can do whatever you want. So by encapsulating kind of your calls to asm, you can really take away a lot of the pain of kind of interacting with this. At the same time, you still get the benefits, especially the performance benefits of being able to do these kinds of things. So once you've done this, especially if you've kind of written a nice wrapper around it, your asm.js code becomes just another module, living right alongside your app code, right alongside your MVC framework or jQuery or any of these other things you might be used to using. There are a number of libraries already, like I mentioned, that have been compiled with some scripting that are already using asm under the hood, that have nice JS interfaces. You might be downloading and using some of those without even knowing that they're using asm under the hood. The visible benefit will just be high performance, perhaps interesting capability, things like that. A couple of odds and ends. The first one is use worker threads. Asm.js, because it only operates on numbers and kind of this heap, it's perfect for putting on a worker. If you're using ASM modules to do any kind of processing, try to do it asynchronously. Run your module on a worker, use post message, send it whatever data you want, send it whatever arguments you need, let the processing happen, take advantage of the 4, 8, 16 cores that are present in most people's mobile phones, laptops, desktops, whatever. Take advantage of all this stuff, let that execute asynchronously, don't block your main thread, send the data back when it's ready, and then do whatever you need to do, whether it's display it, play it, do whatever. As an aside, worker threads are awesome, and they're going to get actually even more awesome. This is really unrelated to ASM, but we're kind of doing this partially because of ASM. At Mozilla, we're looking to push a lot of existing web APIs onto workers. Right now, most implementations have IndexedDB, XML HTTP request, and in some cases, WebSockets available on workers as kind of your main APIs. But we want to push really basically anything that doesn't directly interact with the DOM over there. So we want to let you do Canvas 2D and WebGL over there. We want to let you do WebRTC, both for setting up data channels, for setting up video and audio streaming, being able to process all this stuff. We want to let you do WebSockets. We want to do web audio. There's no reason why you shouldn't be able to play audio from a background thread. And we're also going to be adding the capability to do synchronous message passing, but only between workers. So you can actually have a worker block until another worker responds with the message. Instead of just throwing messages back and forth with no ability to wait for a response, you'll be able to actually say, here's a message, do some work, and I'm going to wait, like this execution is going to be blocked until I get a response back. The reason why we're doing all of this is, again, coming back to, for example, the games example. If somebody is bringing a full C and C++ app that wasn't especially really designed for the web, there's a lot of things that you expect to be able to do synchronously that you can't do on the web. For example, file I/O is the typical one. If you're writing a native app, you expect to be able to open a file, read from it, get some data, close the file. On the web, you can't do that. On the web, for example, using IndexedDB, you can open a database, but then you have a callback. And then you can request some data, and then you have to wait for a callback to actually get that data. That doesn't really map very well to kind of typical app patterns. But if we put this in a worker, especially if we have the synchronous message passing, then you can do kind of all of this stuff. And so the idea is to make it easier to bring some of these larger scale web apps, larger scale native apps over to the web. You can actually run that entire native app on a worker thread and just provided access to the main DOM, main HTML page for doing its display, for doing user input, for doing events, but have the bulk of it run on a web worker. This will also, again, once you actually get things like WebGL, this kind of stuff, this becomes possible for pure JS apps as well. You can start to think about how do I move the majority of my processing off onto a worker thread so that the only things that I do on the main thread are actually just DOM manipulation. But all of my processing, all of my network requests and everything is going to be happening on this worker thread. Again, for performance, for taking advantage of multiple cores, for parallelism, all of these kind of good things. So workers are awesome. Use them. If you're not, look for ways to take advantage of that capability. The other thing that ASM really likes is asynchronous script loading. asm.js code can be large, and parsing and compiling it takes time. What do I mean by large? So the Unreal Engine 3, high-end game engine, over 1 million lines of C++ code, it's about 36 megabytes of minified JavaScript. 36 megabytes of JavaScript. If you gzip that down, it goes down to about 17 megabytes of gzip JavaScript. So that's a lot of JS. When we first got this working about a year ago, no, actually less than a year ago, about 8 months ago, it took a good 25, 30 seconds to actually parse and compile all that JS. That's a really crappy user experience if you go to a web page and you actually get to sit there for 30 seconds waiting for something to compile. The good news is in the past 8 months or so, that's now down to about 5 seconds. That's still not great, and especially not great if you're doing this on mobile, where those 5 seconds now are back to 30 or 45 seconds, or even, who knows, like a minute, minute and a half, depending on what you're compiling. Especially because you're going to be compiling the same thing every single time. So if you add the async flag to the script loads, most asm.js modules, especially those coming from Scripton, are already set up to support this. All that compilation will take place on a background thread, and you'll just be notified and you'll have your callbacks actually be called when that code is ready to go. As a side effect, and completely transparently to the user, in the very near future, this compilation is also going to be cached. So the actual compilation will only happen the first time you encounter this piece of code. We're going to cache that on disk later on, and so when we encounter that same code again, we're just going to load the already compiled version from disk. So for example, now, that same 16 megabyte compressed code that took 5 seconds to compile, now it actually takes on the order of maybe 10 milliseconds to just load the compiled version from disk after you've done it once. So you actually get a pretty huge speed up. Here I actually wrote in the very near future, and I wrote this 4 days ago, but that very near future turns out to be now, because this kind of landed in Firefox Nightlies 2 days ago. So especially any async asm.js code, potentially some other async code, will get cached to disk and loaded directly from there. This is doubly important for us in places like Firefox OS, where the only apps that exist there are pure web apps. And if you have something that's using asm.js, especially on a low-end device, it might actually take a minute, minute and a half to compile this stuff. But we have the ability with this async script loading and with caching to do that compilation work when you first install the app. So as part of the install process, you download it, do all the compilation necessary, and then when the user launches that app, you get an instant launch experience, and it becomes very comparable to what you might get from a native app on Android or iOS with the same kind of feeling. And because of asm.js, you actually get similar performance as well. So we kind of have the same kind of feel, even though the actual app is just a web app. It's just JavaScript and HTML. So that was a bit of an overview of what asm.js is, how do you actually interact with external libraries through asm.js from your own JS code. I want to give you some examples of what you can actually do with this. I'll apologize in advance because I don't actually have any demos to show you. It turns out I had a lot of really great ideas, but when you only give yourself a day to both port stuff and make demos, things often don't work that quickly. So here's some ideas at least. The first one is you can start to do a lot of processing of image data client-side. If you have a JS app that lets the user upload an image, Facebook is kind of the typical example, maybe even something like Twitter. Right now, users will happily drop their 30 megapixel, whatever DSLR JPEGs onto your web app, which will then usually happily get sent over to your server, and you'll do a whole bunch of processing server-side just to scale that down into something reasonable so you don't have to store this huge image, you don't have to transmit this huge image back to the user. You can do some of this processing on the client side today. For example, the scaling you could do client side today. You can use a canvas, scale it down, get the image data back, get it back as a JPEG. You have very little control over things like the compression parameters there. And you also can't really efficiently do a lot of image processing. With the help of asm.js, or with any kind of really module here, you can do a lot of things client-side. You can do color correction client-side. With something like OpenCV, you can do face identification client-side and just send that data back to your server. I say, hey, I already found the faces here. You don't have to spend CPU cycles on the server side doing this. You can do scaling using whatever algorithm you want to get a higher quality scaling. You can also do things like, let's say you were to take something like a JPEG compression library and bring that in to the JS world through asm. You can do compression of your image data using whatever parameters you want. You can even maybe let the user control the quality, control various other settings to get a high quality compressed image, as opposed to just relying on whatever the default is that the browser gives you when you call, toblob from the canvas element. You can push a lot of data analysis down to the client. So instead of having to do a server-side round trip to do any kind of complex analysis of data, let's say financial data, medical data, whatever the case may be, you can instead push the raw data down to the web browser and do all that processing client-side because you have the performance with asm.js. Performance generally tends to be within about 2x of native. So what that means is something coming from C and C++, compiled with some script and running in asm.js, tends to execute at about half the speed of native code. That sounds kind of crappy to say, because half the speed, that's really slow. But that's actually good enough for pretty much anything. I mean, computers today are fast enough that when you're talking 2 milliseconds natively versus 4 milliseconds in the web, all the advantages that having that on the web easily negate that 2x kind of performance factor. So you can start to think about what data analysis can you actually push down to the client. What can you do by just having the raw data there and then doing any kind of operations on it directly there instead of using up, again, CPU cycles, potentially saving money in hosting, all of these things. Some other examples. This is actually one that I really wanted to do a demo of, and I might actually do this anyway. Face login, or at least kind of user confirmation with face recognition. So right now, websites, you have a username and password, you have the little remember me checkbox. It'd be kind of cool if that remember me checkbox also, when you went back to that site, it used your camera and kind of recognized your face and said, yes, I remember you. Not whoever else might be using your computer at the same time. You obviously can't do this for kind of full login to a website. I really do not want my bank using my face or my picture, as somebody might have it, to log me into my account. But you can do this for confirmation. And would also make the site feel high-tech, like face login and all these things are kind of really being popularized by PS4, Xbox One, all of these things. And the ability to do that on the web would be a really cool thing to be able to show off. You can do things like add text-to-speech. There is one quite good open source text-to-speech library that's actually already ported to Emscripten. It has an Emscripten and a nice JS API already existing. And so you can use this to do things like read notices in the background. For example, Twitter could happily tell you that you have 5 unread messages, 7 unread messages, 10 unread messages, 100 unread messages, and then you'd probably want to turn it off because it'd get kind of annoying. But any kind of notices that you might have, you can provide them in the background this way. You can use interesting ways to give oral clues to the user. Maybe if you have a tutorial on kind of how to use your site or some kind of help, you can be reading that in the background while the user is interacting with the site. Some other examples. You can implement new image, maybe even video codecs using this. The web right now, you generally have JPEG, GIF, PNG, and then a bunch of kind of smaller, less commonly used formats. You have something like WebP also in some browsers. It's very hard to get a new image codec standardized on the web and especially available in browsers. But with something like ASM, it's actually fast enough to do that decoding, especially for images, directly in your JS app. So if there is a codec that is, for example, specialized, there's a number of codecs for line art out there. Browsers don't provide native support for them, but they provide very high quality compression and also very good compression of very specific types of images. You can use asm.js to bring those codecs directly to the web. You would, instead of an image, you would have a canvas at the beginning of your load, or actually you could probably just write image tags. You would scan the document for all the image tags, look for the ones with the extension of your custom codec, replace them with canvases, send off all those images over to a worker thread for decoding, send them back, draw them. It will be transparent to the user, but you can then have a lot more control over what codecs you use for your site. If your app is dealing with a particular type of image data and there are more optimized codecs, you have the option to do that. I put a video in a question mark here. There's a company called Otoy that's doing a codec called orbex.js. There were some press releases around this. This isn't, it's unfortunately not open source, but it's interesting technology nonetheless. They have a video decoder written purely in JavaScript, taking advantage of both asm.js and WebGL. And they're getting quality equal to or better than H.264 and similar performance, running purely in the browser. And they get to do some really cool things with this, because if you can ship the decoder to the user, you can do things like watermarking, you can do things like customization per user, things like that, much more easily than if the browser had to support each individual codec directly. And something simple, for example, if you're writing a mobile app or a mobile web app, or even a web app that happens to have a mobile component or mobile optimized version, you can do things like recognize barcodes. Again, you can use WebRTC in the camera along with some barcode recognition to be able to kind of scan a barcode on your mobile app and make it feel and have the same capabilities as a native app might have. Performance, like I mentioned before, it's within 2x of native, and this is actually pretty consistent. We're finding that performance rarely varies more than this. Sometimes it's faster, sometimes it's slower, but starting with any arbitrary piece of code, especially from C and C++, especially any kind of algorithmic library, once it goes through the process, once you get it on the web, it's usually within 2x of native. So you can kind of get a good idea of what things might perform like on the web when you plug them into your web app just by looking at their native performance. And even on mobile. And this is a pretty big deal, like I mentioned, on Firefox OS and even in any kind of mobile web apps, because you can make your mobile web app feel a lot more like a native app, both in their capabilities and also in its performance. So really the two things you need to start taking advantage of some of this stuff or some of these modules in your own apps. The first one, you need some familiarity with C and C++, especially if you want to take advantage of the existing libraries out there, open source or closed source. Or you need somebody nearby familiar with C and C++. You don't need a lot of in-depth knowledge. It's not extremely complicated to do some of this porting and compilation work, but there is going to be some glue code that you will have to write, at which point familiarity becomes very useful. And then you just need Emscripten and the Emscripten SDK. Open source tool, free for general use. You can just download it from emscripten.org. This is not just for C and C++. The focus has been on C and C++ due to the large body of existing code out there. Lots of libraries, lots of apps that really want to wait to get to the web. But like I mentioned before, there's implementations of Python, of Lua, things like that, all out there. One example of how you can use this is, and this might sound sacrilege to say, but in a web app, you could give your users the ability to write scripts for that web app using Lua. Why would you want to use Lua? Well, maybe you actually want the extra security by providing a very explicit barrier between your JS code and the user code. There's a lot of sandboxing things you can do in JavaScript. Sometimes you get them wrong. By using a completely different VM, you can both give users maybe slightly easier language to work with, especially if they're not technical, but still let them extend your app in interesting ways. So to wrap up, the resources for all this stuff, asmjs.org for asmjs itself has information about the asmjs language, the spec, FAQ, things like that. And then emscripten.org is actually probably the main one. It has information on the Emscripten C and C++ compiler, as well as a lot of projects that are using Emscripten, that are using asmjs, both whole app ports, but especially a long list of libraries that have already been ported and made available to JS and the web through Emscripten. So that's all that I have for you today. I think I still have about 5 more minutes or so for questions. Any questions? Nope. Right there.
Like you're talking, like it's like the team is like giving a lot of stuff to the client side. And like this is the same thing that I was thinking about, like when data local storage came out. Like how do you leverage like security and like data confidentiality, like just passing everything?
So the question is, how do you maintain security and data confidentiality by passing everything to the client side?
Or like what you write yourself. Like you don't want people to spend time making.
Oh, you mean like how do you maintain a confidentiality of your own code if it's all kind of living on the client? That's kind of a typical problem, well, not really a problem, typical challenge you have on the web today. We found, even when we were talking to people who have native apps that they're looking to bring to the web, when you actually show them what kind of minified, obfuscated JavaScript looks like, it doesn't really matter. It's very hard to go from that back to anything you could actually reuse or copy. So if you're really concerned about kind of making sure that nobody can kind of steal your intellectual property or reuse kind of your work, running it through minifier, running it through some of the JavaScript compression, obfuscator tools out there, generally tend to do away with that concern. Once we've kind of shown that concern has really kind of gone away. Any other questions? Oh, right there.
Are there any other kind of killer demos other than the Unreal engine?
Are there any other kind of killer demos other than the Unreal Engine? It depends what you mean by killer. That's definitely the most kind of visually flashy one. There's actually going to be some product being launched commercially on the web based on some of that work over the next couple of months. There's a bunch of demos of some of these libraries. For example, there are demos out there of things like text-to-speech, speech recognition, image compression, video codecs. All these things are generally out there. They're not as packaged in kind of a flashy way, but I was actually playing with one of the the speech recognition demos yesterday, that it's sort of doing live speech recognition in JavaScript using WebRTC. I didn't want to show it because for whatever reason, the microphone in this laptop was just not being very happy. But you're speaking and it's kind of with maybe a half-second lag, it's doing the recognition there, which is kind of cool to see. It's not as flashy as going around shooting things, but it's still pretty neat to see that happening in a web page. Yeah.
When you talk about browsers starting to cache compiled asm.js code, what are they going to be actually caching? Some sort of bytecode?
That is a good question, and I don't know the answer to that. The engineer who wrote that, Luke Wagner, he's actually the author and designer of most of asm.js. I'm not sure what he's caching. Oh, sorry. The question was when the browser is caching compiled asm.js, what is it actually caching on disk? Is it caching bytecode? Is it caching native code? I'm not sure. It's definitely one of those two. He might be caching the resulting native code directly and then loading it and doing some patching on it first. He might just be caching the parsed bytecode because then it's very quick to just generate native code from that.
Can I ask a follow-up?
Yeah.
So, I mean, does asm.js use actually a separate runtime, or is the runtime optimized for that subset of the language? Like, how is it actually implemented?
So the question is, does asm.js use a separate runtime, or is the runtime optimized for that subset of language? It's the same runtime. Asm.js code runs in the exact same JS runtime as all the other JS. It's just the parsing and code generation phase of the JIT that's optimized for asm.js. But once the code is generated, it's living in the exact same world as the rest of the JS. So it's more kind of just the front parts of the JIT that are optimized for JS. There's a question actually in the back there first.
I was wondering what the state of LLVM compilation to asm is, if you know if people are doing that so that you can compile any LLVM language.
So the question was, what is the state of LLVM compilation straight to ASM? There's kind of multiple parts to that question. So Emscripten itself uses all the LLVM front-end machinery, and the Emscripten translation runs after the full kind of link phase has been done. So in theory, it should be possible to take another LLVM language and already run it through Emscripten at the back end. In practice, I don't know how well that works because it's really been optimized and tested mainly with C and C++. However, we're starting up an internal project now to actually implement Emscripten as a direct LLVM backend, so without having to do the separate Emscripten step, which should make that much easier.
I just want to understand. So suppose I wrote function C++, and then this is going to a basic example. And then asm.js is, what is it going to do? It's going to port that C++ function into some JavaScript function?
So the question is, let's say you have a C++ function. How do you actually get access to that in JavaScript? What's kind of the process there?
So once I execute that function in JavaScript, what happens to the C++ function?
Right. So the process that you follow is you start with the C++ source, and then you use the Emscripten compiler to generate a JavaScript module. So you would run on the command line emcc myfile.cpp output to myfile.js. Now you have a JS module, which you would then take in your web page. You would just load it with a normal script tag, and that JS module would export whatever your function is.
And why would that JS module be faster?
Then which?
Then suppose I wrote that function just plain JavaScript.
Okay, so the question is, well, why would that module and that function be faster than if you wrote it in just plain JavaScript? The reason is that the type information that asm.js especially provides lets engines really highly optimize the code execution. Regular JS, engines spend a lot of work doing a couple of different things, one of which is trying to guess what the types of everything is. If something is an integer, they really want to keep all that stuff as an integer for performance.
So it kind of optimizes your JavaScript by doing these types.
Yeah, it optimizes your JavaScript and optimizes the final code generation to give you kind of the final, most highly optimized form.
Oh, so in the end, it's just JavaScript, but it uses the C++ information to optimize it.
Yeah, exactly. In the end, it is just JavaScript, but it has a bunch of extra information that came from a highly typed language like C++, to provide information back into the JavaScript runtime on how to optimize that. Yeah, it's a good way of putting it. All right, I think I've got time for one or two more questions. Okay, one more question. Oh, right there.
All the worker features you were talking about, synchronous message passing, WebGL, WebRTC, what kind of timeline do you see on that?
So we have WebGL and workers implemented right now in Firefox nightlies. Actually, I don't know if it's landed yet or might in the next couple of days. Everything else is scheduled probably for the next 2 months or so. The way our release process works is we sort of shift from nightly to alpha to beta to release every 6 weeks. So basically, now, 18 weeks from now, WebGL should be in released versions, and so maybe another 6 or 12 weeks after that, we should see the other things.
And are you synchronized with Chrome in any way? When would I see that info? Because for us to build WebGL and
Yeah, right.
it needs to be in Chrome. I mean, who knows what Apple
Right.
Chrome.
We're in pretty close communication with a bunch of Chrome folks on a lot of this stuff, everything from asm to WebGL to the worker capabilities. I don't know what their timeline is for some of this stuff. They know that we're doing the work, but I don't know what their internal plans are for when they're going to get it out there. Cool. All right, thank you all.
Thanks, Vladimir.